when I said it's good not to stop looking at something. I don't have much profound to say, but I want to say a few more words about the homework that we discussed yesterday. Just to see that, to show you that if you keep staring, then you can see a little more than what you were seeing, just that we can see it a little more elegantly, okay? There were some questions yesterday. And why do I want to talk about this? Because the example of the first problem, well, both are kind of extremely illustrative. The first problem, it's sort of a prototype of what happens when you have more than one of the same Higgs structures, like the possibility of two Higgs doublets in the standard model, okay? So it's good to understand it deeply. So when we look at these two, no, it's not a good shot. It looks good. It feels like good. I can say it tastes good, but it's not good. So I don't know, maybe it's not here. They're very similar. Maybe this one. So, so we have these two triplets. So which case I took first? B, I think. And I wrote phi 1. I said the better notation would have been this one. This was the case B when they are parallel to each other, which meant that lambda 4 was negative, right? Because then we wanted. Why was this? And then you know you can use the symmetry argument that I keep telling you, because if you want to solve the problem of symmetry breaking in SO10 or make it worse, of an exceptional E6. Imagine that you study E6. I don't know how much you know about the group, okay, which is a very tough group. You don't know how to visualize it, okay, and people even study that. Actually, a PhD student of my collaborator, Boris Baitz in Ljubljana, did a whole PhD on that, okay. And then you have to sort of use group theory. You have to use symmetry arguments in order to understand what is going on, especially when you want to compute the masses. So we said here, there is, for example, there is an SO2 symmetry, so I have a complete symmetry between G1 and G1 prime. Okay, this will help me. And then there is a 1-2 symmetry, obviously. When V1 goes into V2, I have a symmetric situation. So, for example, the states that we found out. Okay, we found out that they are following Goldstone bosons, number Goldstone bosons. V1, G1 plus V2, G2. Why is this a Goldstone boson? Well, when V2 is 0, this has to be G1. Okay, the Goldstone boson is going to lie in the multiplet. We said that. I said that yesterday quickly. Okay, in the multiplet where there is symmetry breaking, and vice versa. And therefore, this is the linear combination properly normalized. Okay, the weights are going to be V1 and V2. And because of the symmetry G1 and G2 prime, the other guy I can read off immediately. Let me call it G prime. Would be V1 G1 prime plus V2 G2 prime divided by square root of V1 squared plus V2 squared. There was no need to compute, strictly speaking. I want to show you. Then we found two massive states, right? H was orthogonal to G. I don't think I have to write it, right? V2 minus V1. So this notation I'm going to reserve, and H prime was orthogonal to G prime. And what I know is that when, and this is very useful, when lambda 4 goes to 0, limit, then I have two worlds which are completely separated. Therefore, the symmetry now is increased. I can separately rotate phi 1, and I can separately rotate phi 2. Therefore, the symmetry is SO3. In this limit, the symmetry is SO3 times SO3, which is broken down to, you did it? Each case will be separate. You would have two problems, two homework problems. Right? They don't talk to each other. There is nothing to do. So that means I will have 4, 2 plus 2, 4 Nambu-Goldstone bosons. Okay. Right? In this case, if lambda 4 is 0, these two are Nambu-Goldstone bosons and these two are Nambu-Goldstone bosons, or any linear combination thereof. There had to be 4. So that means that these two guys, which must have, which will possess this 1-2 symmetry, they must be massless in the limit lambda 4 going to 0. It's going to be lambda 4. There is a normalization over 2 in our. That's an important normalization we can fix with a little thought of how we normalize the states. Okay? And V1 and V2 enter symmetrically. There is no difference between those two guys. It's going to be like this. And lambda 4 is negative, therefore it's going to be like this. Otherwise, this would not be a stable local minimum. Okay? Sorry, when lambda 4 is 0, I have to recapture 0. They must be massless. These are the 2 extra Goldstone bosons that I miss. Because in this case, there is absolutely no difference between any linear combination of these two guys. This is my SO2 symmetry. The notation is irrelevant. Okay, sometimes when I write down the Goldstone boson, there is a symmetry that doesn't mean much the way I wrote it, because any linear combination will be. Here I've broken that symmetry, okay? SO2 cross SO2, there is SO2 symmetry, that is true. But that's an overall SO2 symmetry that involves both guys. And therefore, in that case, you see the Goldstone bosons are the mixture of the guys that live in different multiplets. There is just one SO3 and one SO2 that remain, and one set of Goldstone bosons. Okay, is that clear? Okay, I just wanna, we could push it. Okay, this is of course not the way you understand it. You first compute typically. But next time, maybe when you do SU5, if you really sit down to do SU5, I give you a hint. Please use the remaining symmetry. It will help you computing masses. There are 24 particles in a joint of SU5. Are you going to compute 24 masses? No. If you give it a thought, you will use the remaining symmetry. Okay. Imagine that I break SU5 to SU4, then I would say, SU4 is a good symmetry, therefore there will be a multiplet of SU4 that has to have the same mass. Okay. So I pick up one guy. All right. I don't know if I have something intelligent to say, but maybe let's check about this case.
But first, in this case, then, how many links do we have here? 2?
Oh, I didn't finish. These were these guys, which were easy to see. I didn't have to compute at all, right? And then there is a system H1, H2. So what I noticed in this case, when they are parallel to each other, that there is no difference between lambda 3 and lambda 4 coefficients, couplings. Lambda 3 was this. Let me write symbolically. I think you understand that. These are our vectors. And lambda 4 was this. But when they're parallel, these two guys are equal. Okay? There is no mixing angle between them. There is no vectors like this, and therefore it's the same. Therefore, I know that the thing that then enters here, the relevant coupling is lambda 3 plus lambda 4, not individual. I can just take it out, so it's going to depend just on that. Okay, okay. There is one little calculation. When this coupling is equal to 0, then these guys, when there is no mixing, then I have again the situation that you studied in your homework. So you go back in your homework and you see that the mass was lambda 1 lambda v squared. That would have to be the mass of that guy if there is no mixing between them, because then this triplet would live alone, separately from the rest of the world. the Higgs in the triplet, sorry. And similarly, there will be another guy. You call it 12. Maybe there is a factor of 2. Let me not worry about the normalization. You look up at your notes and you say, oh, I computed this, I don't have to compute. So the mixing, where is the mixing coming from? It has to come from these two, lambda 3 plus lambda 4. And maybe then you say, aha, and of course it's symmetric in V1 and V2. Okay, there is a little computation, but almost nothing. Okay. I wonder if I had to say, let's see if I have to say anything about the other case. Okay, maybe just on the 4 positive, phi 1 will be the ID's notation, okay, and you will see there was maybe something not perfect about the notation, something even now, and phi 2 is then G2. V2 plus H2 and G2 prime. So now they are orthogonal to each other. This guy, I wonder if I was clear, and this guy live outside of symmetry breaking. These are those guys that come from phases, these come from the broken generators, okay? These guys got to be Nambu-Goldstone boson. You have to remember how to recognize the Nambu-Goldstone bosons. In the case of a complex field, there was just IG. There was the guy which was orthogonal, there was a real and imaginary part. Okay, they were from separate worlds. Remember, when you have one triplet, you can always write e to the I, gi, ti over v. Just to remind you, 0, 0. V plus H. Okay, these are the Goldstone bosons, and you will see they will end up living here because they are broken generators, okay? They will not end up living here. The guy that is here is unbroken, they will be here. And you would check, let's see, G1, T1 has 2, 3. I think it goes like this. G1 ends up here. My notation is not perfect, and you will get minus G2 here, something like this. Because there is signs there, okay? That you can check on your own, okay? I'm pretty sure. Just to remind you, T1 is 0, 0, 0, minus I, 0. So IT1 will have plus 1 here becomes. And minus 1. So T1 would be, you know, it will leave the guard here. It's the second row when I multiply. And T2 you will see that they give you a sign there. Why am I saying that? Because what happened, okay, just so that you could have kept staring, okay. So these two are, and then one linear combination, okay, because now we know that there are 3 Nambu-Goldstone bosons, not 2. The symmetry is broken completely. And there will be one linear combination of the guys that remain. And it was interesting, the linear combination that we got, and you can use the same argument that I used before, so there has to be, let's call it G3. G3 would be, it says here, G1 prime, strange. It says G1 prime V2. No, I'm not sure. Does it this look suspicious to you?
Where is it 3?
Huh?
What is it? It is a number boson.
Right. G1, G2. And so the third guy I call G3. I don't like what I wrote. Imagine that V2 is 0. What should be the Goldstone boson if V2 is 0? It should be this guy. So this looks suspicious. If V2 is 0, I get that G2 prime is a Goldstone boson. That's suspicious. So I don't know what I wrote. I think it should be this. Once again, there is this logic, right? The Goldstone boson, you recognize it the case when the web is 0. Then you say there is a symmetric linear combination. The only thing you say, well, why is a minus sign here? And the minus sign is my choice of the names that are given here. The Goldstone boson go as these phases of the generator. So if you were written carefully, okay, you never know, okay, then you have to think twice, okay? It came out okay because I had the same convention here. It could have been wrong. Maybe I should have called this minus G1 prime or minus G1. It's irrelevant because that's just an overall sign, okay? I have a symmetry, SO2 symmetry here, which is protecting me from an error. So the combination is coming with a plus sign because even if I should normalize this with a minus sign to be careful, okay, both of them will go equal. But here, as I showed you, when you write like this, then you have to think, what name should you give this guy in order to read off very quickly what a Goldstone boson is. That's all. Okay. So once this is, then you say there is a Higgs, which is orthogonal to G3. You agree?
Mm-hmm.
There must be such a Higgs. And the mass of that Higgs. Okay, I'm going to send you these notes later. There was no time. I'm better. Then again, by the same logic, when lambda 4 goes to 0, that's number Goldstone boson number 4. So the mass of this H guy, like before, must be proportional to lambda 4 with a plus sign. Lambda 4 is positive now. The symmetry tells you that you're going to get the webs contributing equally, and so on and so forth. And then you do H1, H2 system. In this case, lambda 4 doesn't contribute at all because they don't mix. They're orthogonal. So if you look at the wet nodes, you will get the same thing we get there, but there'll be only lambda 3. And the same logic can be repeated. So I wanted to show you the nodes are called the power of symmetry. Okay, more. The example is sort of trivial, easy. It's simple, but when care is taken, when an attention is paid, there is always something to see. Now, problem number 2, which is so important. I want to correct myself. Well, I'll ask a question. I said something yesterday which was not completely true. Or actually, it was wrong. It's a euphemism of saying that. There was, who was complaining? Guillen, I think, was complaining, well, computing gauge boson masses. I have to do this, no? So I did Mathematica. I think it was you. Yes. Right? So, and I was trying to argue that it's not that that's like problem number 2, which I'm doing upside down. I'm first looking at gauge boson masses, okay? Because that's safe. The way I phrase the problem is for you to look first at the Higgs, okay? Because if you look at the gauge boson mass, you see immediately what is going on. There you cannot fail, okay? The symmetry break-in is then well dictated, is given by covariant derivative. And I said that I got this. Where the web of the adjoint of our SU3 is a diagonal of this form. So let me just show you how. Okay, in order to get this, you have to do this. You have to commutate, right? The covariant derivative of sigma, we said, is d mu minus ig ta a mu a. A ti are just Pauli matrices in proper places, okay, plus Cartan. If you want to do SU5, it's the same thing. There is just more of these Pauli matrices stuck in various places. But the generators of SU5 are the same, or SO127. You put Pauli matrices 1 and 2, wherever you can put them. And you will exhaust always the number of generators minus Cartan. The rest is just Cartan, which of course traces diagonal matrices, okay? Then you say, oh, but there is a lot of commutation to do. Okay, so let's do a little thought. Look, when A is equal to B, these have to vanish. Why? Because then the symmetry is SU2 cross U1. So these two guys must be proportional to A minus B squared. In this case, sigma 0 would be, let's write it like this, 1, 1 minus 2 times some, let's call it V. This manifestly preserves SU2. It's a unity. Remember, sigma 0 transforms as sigma u sigma 0 u delta. This preserves SU2. Or if you wish, the generators act as commutators. So let's write I. I1, 2, 3, you see, immediately commutes with a unity matrix in SU2 space. So therefore, in that case, okay, this will be massa, so it's proportional to A minus B squared. So when A is B, in this case, so let me check if A is B, we had a relation that A squared plus B squared plus AB, we get immediately was M squared over 2 lambda, right? Where the potential was minus M squared over 2 trace sigma squared plus lambda over 4 trace sigma squared squared. It was a very simple potential. So what do I get when A is equal to B? A squared plus A squared plus A squared, 3A squared is M squared over 2 lambda. Now what are the mass of these guys then? A4 squared plus A5 squared. Of course, it has to be the same. This is just a doublet of gauge bosons in the SU2 language. Okay, it's actually the physical states are linear combinations: A4 minus IA5 and A4 plus IA5. Hello. So they have the same mass, which is there was lambda, no, which is 1/2 G squared, right? Times, what will I get? Two A plus B, that's 3A, that's 9A squared, or something, no, 9A squared. But that's just, okay, let me read it. We can read from here, okay? Then A6 squared plus A7 squared is 1/2 G squared. You would expect G squared, okay, one thing that you don't see immediately is the coefficient. But A is equal to B, so this is the same. Of course. So again, you get the same mass, 9A squared, with A squared given there. Why do I get the same mass? And I didn't have to compute that, I want to argue. That's in SU2 symmetry. Remember the octet of, this is the octet of pions and kaons, exactly the same quantum numbers, right?
Yeah.
This adjoint representation of SU3 should ring a bell. What were the states in the, what were the octet of mesons? Pi 0,
5 plus,
pi plus,
5 minus,
pi minus,
5 plus, k plus.
right? This is T3 here, hypercharge. Then there is K plus,
K0,
K0 bar.
K0 bar, K
Minus.
K0 bar.
something like this. And there was eta,
And
the singlet. So these two guys should have the same mass. This is K plus K0 and K0, K minus. And they do have the same mass. So if you use you know, and I have number of states, okay, I had 4 states here. This one is massless. So I know its mass must be proportional to A minus B square, okay, I'll hint to that in a moment. You don't have to do so many commutators, what I want, just take one. These 4 have all the same mass. All you have to do, take is one generator and commute with your sigma 0. Pick one, A6 square. A4, A5, A6, A7 will have the same mass, the same way the K plus, K0, K minus, and K. Before you compute the KK bar mass difference for the Beach interaction effect, okay, they of course have the same mass by the pseudo-symmetry there, which remains there. Now, if I use, I'll send you the notes so you can give it some more thought. Suppose I take 2A plus B equal to 0. Again, the symmetry is SU2 cross U1. But it's a different spacing, we said. So this guy would be massless then. These guys should then have the same mass, if I'm right, if my reasoning is right. And you will see that they do. And you will see actually that you get the same thing, because it doesn't matter where you put SU2. So there was just one calculation, if you wish. You could have done it each way. If you recognize this particular linear combination, they have to vanish when you go to the SU2 symmetry, okay? It was enough to compute this term, for example, the coefficient for A1, and then the rest would have to follow, okay? So the symmetry can be and should be used when there is computational tedium.
But the problem was actually reaching this formula.
I'm saying no, there was no problem. Well, you know that the generators are commutators. So you say there's a lot of work. I have, I don't know, a bunch of gauge bosons to do commutators, and then I use the SU2 reasoning, and you will see that you have to compute one coefficient, and then the rest use the symmetry argument.
I mean, to get the masses, but I mean, to get the coefficient of A minus B all squared to A plus B all squared.
Well,
We still have to do
well,
some
notice that when A is equal to B, then these guys would,
They carry dimensions, they carry dimensions, so they have to be squared.
yeah, they carry dimension. This is just the web basically squared, a particular combination, okay? And why these combinations, okay? Just because you realize when A is equal to B, that the SU2 cross U1 symmetry is in the first 2 components. Then when 2A plus B is 0, you have to think a little bit, okay? I'm not saying when A is equal to B, the web is like this, 1 minus 2. You say I have an SU2 symmetry, let me use it. When 2A plus B is 0, so B is minus 2A, so then it looks like this. Again, there is an SU2 symmetry, just in the 1-3 space. Okay, so I notice that there is a parallel between these 2 statements. The same way when 2B plus A is 0. In this case, you will get it here. 1 minus 2. And so on and so forth. And then you use the symmetry arguments every time it's SU2 cross U1. Notice that whatever I do, I will get this 9 a square with 3a square is okay. There is just one, basically one thing in general.
One
But
question. That is,
you can do better than that, huh?
that is in the case that mu is not 0.
Right.
Then that is not the
The
vacuum.
mu is 0. When mu is 0, there is nothing, there is just one vacuum.
You're just doing when mu is 0,
Yeah, of course.
A is equal to B.
But I'm using reasoning to check my coefficients.
But
No, I'm not using A equal to B. Look, this is my expression. But I'm saying that, how do I know this is going to be proportional to A minus B squared? I'm lazy, okay? You know, Guillermo says, well, it's a lot of work. I have to plug it in mathematics. Okay, you can do that if you have mathematics. I'm just like saying I can use symmetry argument to avoid this.
But in,
I don't know how to use mathematics. Let me put it this way.
but,
I don't.
but in the
I'm a
case of,
computer idiot.
but in the case of mu equal to 0, everything is this done.
Yeah, of course, but when there is no 0,
Okay.
then again you can use reciprocal symmetry.
But one question. That's what I thought there were just 6 non-Boson and not 7.
Well,
Because that sigma 0 is a linear combination of T3 and TA.
Right.
So that made me think that
Oh,
the symmetry was broken in T3 and TA. So these two. I mean,
Good. Okay, so you're making this point.
but in the sense that you have like this T, S of 8, and then you break these.
Well,
two.
you didn't have to notice that. So that required some sophisticated knowledge or sophisticated thought. Okay, but let's do what you are saying, which I wrote in my notes. You could write sigma 0 as, I don't know, x sigma 3 over 2 plus y sigma 8 over 2. Lambda, why is sigma? Lambda 3 over 2. I think I wrote sigma, I'm sorry. Lambda 8 over 2.
This can
And I get that this is A minus B, lambda 3 over 2, plus square root of 3, A plus B, lambda 8 over 2. Maybe someone did it like this?
Yes.
Well, Jorge said.
Just one last thing. I understand that by doing this you get cross terms, and then you can diagonalize the matrix and see that there is a zero. I mean a mass zero.
No, I want to use reasoning. No, there will be no cross terms. So the symmetry breaking, you see, where is the Higgs typically? I told you always in the direction of the wave. Okay, Higgs is the guy that accompanies the wave. This is the Higgs boson. Okay, this is how the reasoning went. Because of the tunneling, which is forbidden in field theory, there is no tunneling between the general vacuum. I have to live. Whenever there is a valley, we said, you know, whatever the valley is, I got to live here. And then I simply write my field, whatever it was, as, and I call this V, say, and then this shift I call H. So obviously, Higgs is the guy that accompanies the wave. Okay, we said this is a generic principle. So who is going to be the Higgs here?
Both.
Read, please. A minus B, phi 3. This guy carries field phi 3 plus square root of 3A plus B, phi 8. I did a calculation. I didn't even have to do the calculation. I could have guessed that immediately. This is the linear combination against the mass, and you find that. The thing which is orthogonal, call it G7, has a mass 0. It will never appear in your equations if you do correctly the because the way I was reasoning yesterday, I said A is equal B, it has to be, okay, I was checking. I didn't do the whole thing. Because you can say, well, how do you fix the coefficient? When A is equal to B, the Higgs has to be in the lambda 8 direction, okay, that's phi 8. When A is minus B, you will see that it has to go in the, when A is minus B, the wave would look like this. This is the direction of phi 3. Okay? So I said by reasoning, I knew that such a linear combination. I can do better than that. I can compute the direction of the web, and the Higgs will be the guide that accompanies the web. Okay? Right? Because you write sigma is lambda I over 2 phi I. So with lambda 3 goes phi 3, and with lambda 8 goes phi 8. This is the Higgs. The 7th gauge boson was, and what you can remember, okay, I don't want to prove that because that's a delicate, there may be more than one state. If you forget the SO8 argument, what you notice here that there is a flat direction, what we call. A is not fixed at all. So there is a freedom and there is a complete, any arbitrary real number is good as any other number, okay? There is a sort of one whole direction of equipotentiality, if you will. It's not surprising that there is a Goldstone boson associated with that. Forget the SO8 argument, okay? This is typically what happens, and when you learn some supersymmetry, well, I don't know whether there'll be time in that course, or maybe there will be. This is typically what happens in supersymmetric theory. You get these flat directions in the potentials, and then you tend to get particles. They are not called number Goldstone boson. There is no symmetry associated with that. Okay, there may be a flat direction without any special symmetry, but the flat direction is typically because when there is a symmetry, there will be surely a flat direction. That we can call a flat direction. Potential is flat there. So when there is a symmetry, there is a flat direction. When there is a flat direction, there may not be symmetry. Okay. That. So the point of this little exercise was that there was less to compute than it looked. But I would be much happier, let's see how you did it, if you actually did compute. Okay, enough is enough, we have to move on, or we have to move on, but maybe to recapitulate the importance of mixing. Let me go on. But not too far. I'm sort of making a big fuss out of people mixing, right? Yeah. Maybe disproportionately it could seem. And I'm overemphasizing important. Obviously, when there are masses, there will be mixing, right? But it's sort of, there's a profound message in this little mixing angle. That this provided a great window, which has to do with flavor violation, right? If there is mixing, then flavor can be violated. I can go from one generation to another, or from one flavor to another. And this was the great window to new physics. This is how charm had to be there. Without charm, the whole thing of mixing wouldn't have worked correctly, right? So it was a profound implication that you had a new particle with properties specified completely, okay? So the Cabibbo mixing took us to charm. And even in the original G paper, you will see they don't compute it, they estimate. And they are not completely stupid, okay? Glesher, Ilopoulos, and Mayani. And they will tell you that M charm is less than few GeV. And some years later, I said in 74, Lee and Gaillard and Lee will actually compute this box diagram that we talked in the class with the charm walk in the loop. SD symbolically written. And they will come up with the number about 0.5 GeV. A great success of the standard model renormalizability, right? Once you specify your theory, everything has to be calculable. And then even more remarkable, a simple-minded, elegant approach of Kobayashi and Mascara, right? In some sense, so simple-minded, but with a profound consequence. We need to have CP violation. We found out with 2 generations that the CP phase was 0. So then they say, let there be 3 generations, top and bottom edit, and they found out there has to be a phase. And it turned out that some years later, this is 72 when they write a paper, 72, 73, maybe published, okay, in 1972. Bottom quark took about 5 years. In 1977, bottom quark was discovered. Top quark took a long time because it's very heavy, so we are going all the way to 96. Okay. And B, it took some time because they were heavier, and B about 5 GeV, a bit less. And then top, you guys seem to know this number, about 175 GeV. Now let me see if you guys remember the lesson that we said, very important lesson, that if I want to have physical effects, okay, due to the mixing. So for example, when I compute K bar mass difference, so why don't I just say delta and K? You are saying without computing, you guys now know, this will be proportional to sine square theta Cabibo, it went quadratically. And then it had to go as the, and it went like mass square, m cham square minus m up square. And on dimensional grounds, if a dimensional quantity appears dimensionless, this should be cut off by nw squared. The heaviest particle in the loop is W, so obviously the scale that matters here is the W mass. Right. This is the physical scale that corresponds to this value. So for example, you could have told me, look, we are lazy, we don't want to do this loop. If you don't want a precise coefficient, this is going to be alpha over 4 pi. There'll be sine squared theta Cabibo. There'll be G Fermi. How do I know there will be G Fermi? This is a dimension, tell me dimension. What is the dimension of this operator, we often call it, of this amplitude? 6. Fermionic fields carry dimension? 3 times. D5 fermionic field is 3 times. So this carries dimension 6. Therefore, the coefficient has to be 1 over m squared. Okay. Lagrangian carries dimension 4, not Lagrangian density, not 6. And so that's G Fermi. How do I get G Fermi? Because there will be G squared over mw squared that I call G Fermi. And then there must be your coefficient mc squared or mw squared you taught us. So without doing any calculation, okay, we can, this is how they estimate the gym guys, the jump quark mass, right? They didn't want to sit down in that groundbreaking paper, you now have to do the calculation. This will be that effective Hamiltonian, that's called. And then from there you proceed and compute whichever to compute. But I'm here interested in you and I knowing how to estimate the contributions due to the mixing. You will see, because I will ask you a few questions now that or maybe I should ask immediately here in parallel. Let me leave some room. So these were quarks. Why is it that we always talked about quark mixing in those years, for many, many years, and not leptonic mixing? There was almost no mention of leptonic mixing. Of course, from time to time, there will be a genius talking about leptonic mixing. In particular, there is one guy. I wonder whether Smirnov emphasized the name. The father, Pontecorvo. A mind-boggling story, the story of Pontecorvo, who has single-handedly sort of developed the whole physics of neutrino oscillations and the associated phenomena. He thought of the fact that sun may be losing neutrinos on the way coming down because neutrinos could oscillate. He believed that neutrinos had a mass, okay? It's an incredible story. And for a lot of time he was ignored. You know his story, right? He's a unique case in modern scientific history because he was a great physicist that escaped from the West to the Soviet Union. He was a communist who somehow, it's an incredible story, his wife and 3 kids will be smuggled somehow, I don't know, in the hood of the car over a number of borders. Okay, year is 1950, you know, this is a year which you could die for things like that. Okay. And for many years he will be ostracized because, you know, the West didn't want to forgive him easily that he escaped there. The Russians didn't trust him fully, so he had problems getting money to do the experiments. He was more an experimentalist than a theorist. He was the last of the Mohicans. It's often said that Fermi was there, actually it was Pontecorvo. He was the youngest member of that extraordinary school of Fermi. You heard of that school?
In Rome?
In Rome.
Rome, yeah. As a pizza?
No.
No.
Let's see, I'll let you guys try to I'll maybe talk to you a little bit, maybe we'll meet and I'll tell you a little more about that, okay? that in the, before actually the complete rise of fascism, when Fermi had to leave too, his wife was a Jew, he created a great school. And there were a number of people who will get Nobel Prizes, okay? That school is particularly famous for emergence of an unusual genius that never repeated itself, probably, history. I don't know if you've heard of that. Ettore Majorana, who disappeared on the boat ride.
In the lake.
No, there was a boat from Palermo to Napoli. He was originally from Sicily, and he got a job in Napoli. Okay, that's the story. We'll have to talk a lot about Majorana when you want to understand neutrino mass, you will see. Okay, and there was a young kid who came to the school, I think he was 18, Bruno Pontecorvo. By the way, it was Bruno Pontecorvo who will get an idea how to detect the neutrinos. Okay, so these are sort of, and come back to that, remarks on leptons, important. And when we talk of leptons, of course, the main protagonist, the great window to new physics, was always neutrino, right? Why? Because neutrino is crazy, it's completely autistic. Doesn't want to interact with anybody, this is completely crazy. What is the mean free path of neutrinos? Roughly. Mean free path, you know, the distance that you travel before interacting with anybody. So what is my mean free path? Half a meter in this direction, maybe a meter, 3 meters, I don't know, 2.5 meters, right? For electron, it's much less. If you're an elementary particle, it's much less. It's less than a centimeter for an electron. But neutrino, to understand how crazy it is, of course, depends on its energy. So think of the reactor neutrino, which has an energy of MeV, for example. You're roughly. I don't know many numbers, but and I may be wrong by an order or two of magnitude. It's irrelevant. It's around 10 to the 20 centimeters. I remember roughly. Just mind-boggling. Yeah. Two things that are striking in a neutrino is this: the reluctance to interact with you and me. And the second thing, that we wanted to be massless, okay? Neutrino is very light, right? We know today that it's not massless. But the mass is less than 1 electron volt, okay? We'll talk about it. And so if I ask you, why didn't we speak of leptonic mixing so much?
Because of the mass there.
Because any effect, any physics of flavor mixing, now flavor lepton mixing, will be proportional to sine theta leptonic, let's call it, square. Now immediately I go back to 2 generations, okay? As soon as I want to understand something, I forget that there are 3 generations because it's you know, writing things with Kobayashi Maskawa, we notice how unpleasant it is. And what will enter here, obviously, must be proportional. Now we know. And well, a little history of the interesting thing, neutrinos suggested by Pauli, so shyly that he writes a postcard in 1930. He doesn't write a paper, he writes a postcard to people in the Congress on Radioactivity, suggesting that why does he want a neutrino? Why did he want a neutrino? Because of the energy. It seems that funny things are happening here, right? Instead of having a single, right, peaked energy of the electron, there was a distribution energy which would fit nicely with the possible existence of a new particle. He called it neutron, which was to be discovered 2 years later. Of course, neutron was a different particle with the mass of the proton. And then Fermi, gave this his nice name, a small neutron, right? Neutrino. So Pauli immediately regretted suggesting a particle that you cannot observe. He said, we'll never see that. So, and he was a physicist in a true sense of the word, so why talk about things that you can't see? And he was actually Potecorvo who had an idea. He worked in a reactor in Canada I think during the war, okay? Forgive me if I get wrong about detailed, precise years. But he didn't have a chance to do the experiment. That how would you then produce them? You want to see a few events of these neutrinos. So obviously you have to produce a lot of them because they don't want to interact with anybody. But you know that the probability to interact grows with the number of particles, right? It's a statistical phenomenon. So he said, well, use a reactor. And that's what Reines and Coleman did in the 50s. They used the reactor in which you produce in the reactor the flux coming out, I think was about 10 to the 13 neutrinos per centimeter square per second, something like this, a huge number of neutrinos. We could maybe try to see how much you remember in a different occasion. Okay, this is a kind of physics that Smirnov probably must have talked about. Yeah. Okay, this is his bread and butter. It's nice thing that the detector was so small. I don't know if you showed your picture. There was a skinny guy in the, we sort of showed this guy, we could put ears where they could fit there. Okay, so just really, this guy, I wouldn't have fit there, okay, and the others, okay. It was that small detector. You've seen a supercomunicante detector? Which there are boats that go around, in that sort of lake. It looks like a lake, They've come a long way. And the rest is history. This was 1956, so when he was told that they found a neutrino and it was finally confirmed, Pauli says, everything comes to him who knows how to wait. Okay, neutrino physics is all about knowing how to wait. It takes years and years because of this crazy guy, not wanting to interact. So we didn't want to talk, but it was tempting to talk. For example, let me steal some space. I don't know if I want to go back today, but just in case, there was a few more words I wanted to say here. But this is far more fundamental. For example, what kind of flavor-violating lepton process you can imagine? Interesting, that was not observed. What is observed? That muon decays, for example. Well, what is observed is this. This doesn't change flavor. I get an electron and neutrino associated with electron. Then a muon that decays into an electron, remind me, plus. Okay, but tell me, no mu plus nu bar. No change of flavor, mu decays into nu mu. That's the same flavor to us, okay? Yes. And electron goes together with nu bar. Two things noticed here, particularly interesting. Number one, that delta flavor is 0, leptonic. Also, there is no change of lepton number. That's maybe worse. Momentive. That we are familiar with. There is no change of area number in the processes of hadronic physics. There is, however, a change of flavor, as we talked. So tell me the process you would imagine immediately and you start looking for, okay? And it's been looked for. No, proton decay. Flavor, lepton flavor relation. I'm going to make an analogy between quarks and leptons before I move on, just to appreciate the depth of the physics that is hidden in the
oscillations?
Okay, it took a genius like Pontecorvo. You know, Pontecorvo never got a Nobel Prize for because he couldn't do the experiment for detecting a neutrino, which was his idea. He didn't even get a Nobel Prize. He died before it was confirmed. He had a Parkinson and died too early. Okay. For many, many years, he couldn't leave Soviet Union. They didn't trust him. Okay, so it took a long time before he could come back to the West. And it's really a great irony that they single-handedly developed this profound effect. That's very profound to think of neutrino oscillation. You and I wouldn't have thought of that, ever. I can bet you. But we would have thought immediately of or I would have, okay, I'm sorry. What I mean, you start working on your PhD and you don't have to be very smart, and immediately other people said, well, like, by analogy of these processes, I could imagine if I want a muon to decay into an electron and to change the flavor, I want to find something in which I don't get no mu. What could I get here? I want to conserve, say, all the known numbers, Lorentz symmetry, a baryon number. Well, it's easy because there is no light baryon I can put here. Fermion number. So I won't put another fermi, I won't put 2 electrons. Okay, I want to conserve charge. I want to conserve all the sacred symmetries.
Photons?
Photons, for example. There is nothing wrong with photons here. This is the first thing you would expect if flavor is violent. And let's see the, okay, these effects are too well known to you, they don't deserve much space here. How would the diagram look like? This is electron coming out, muon coming in. Then I exchange the W. W changes flavor in general if and only if particles have masses. But neutrinos, we are imagining have the mass, well, you guys know. Let's just imagine they have the mass. So I'll go through some neutrinos 1 and 2. I will change flavor. I can't put it here, gamma. That's a problem. No problem, I put it here. Gamma, W has charge. I can also stick gamma here. I can decide where I stick gamma. But surely this is perfectly okay. So you and I are lazy. What is the branching ratio for B gamma mu E gamma? Right, let's estimate it. Branching ratio, what I mean, I take this decay rate and normalize it to this decay rate. So I say, without doing any calculation, this must be suppressed by alpha over 4 pi. It's a loop effect. Minimum. I don't even worry whether it's square or not. You agree, it has to be suppressed by alpha. And then there is this famous factor, right? There'll be a mixing angle. Here it is. This will enter. And you know, the fact that neutrino mass is less than 1 electron volt was we know that actually delta mu nu is even smaller than 1 electron volt. But knowing that neutrino mass is less than 1 electron volt, what would we have? Let's just imagine that this is less than 1 electron volt square. You tell me how big it is. I don't know what mixing angle is, maybe it's large. I won't write that suppression. So 1 EV, that's how many GeV? 10 to the minus 9. So that's 10 to the minus 9 divided by 100 in GeV, and then squared. Actually, it's much smaller than this. I said this is the minimum. It may be much worse. It may be square. What would I get? 10 to the minus 25. This is why I'm careless. I don't even want to worry whether it's the square of this, whatever it is. Probably the square. This is the amplitude that goes as delta mu square. And it is a square because the number that decides this is around 10 to the minus 50. Whatever. Imagine that it's 10 to the minus 25. The experimental number is 10 to the minus 13. Roughly. Getting there. Improving with the MAG experiment in Switzerland, in Zurich. Yes.
What happened with the neutrinos? They oscillate to the...
Oh, no, I'm not speaking of neutrino oscillations. I don't know anything about neutrino oscillations. It's a profound subject, and I don't know whether I want to talk today about it at all. Let's see.
No,
all I'm saying, if neutrino has a mass, then these are not neutrinos. These are virtual particles. They're not physical particles.
Okay.
In the loop, these are virtual particles. The only thing that in their virtuality is that they have a well-defined mass. Okay. No, nothing. They don't do anything here. Okay. We'll come back what neutrino oscillation means. Okay. By the way, this was the amplitude. You're going to get a square of this. So it's hopeless. But this is why the flavor violation of the electronic flavor violation is so exciting. You will go to conferences very soon, or there'll be talks in the summer when you're here. Because that's a great window into new physics. Imagine that they measure something tomorrow. That's a new physics. There is no way there's some kind of ladder loop effect or whatever hidden physics in the standard model to do that. Okay, so we like processes that open the road to new physics. What other process you can imagine? Just the 3R. You been to Rome? Any of you? Take a walk when you are in the center. It's not far. It's called Via. Now that I've mentioned it, Via Panisperna. It's a little street where this institute was. It's just a little house, okay? It's impressive how little you need to create great physics. Or meet some good people, okay?
Can you think of a process which will change the flavor but without breaking the Lepton numbers?
Oh, we didn't break lepton number. This is the process that changes lepton flavor without breaking lepton number. Lepton enters, lepton comes out.
The total Lepton number.
Yes.
Yeah.
Yes.
And the flavor is
No.
Flavor. Okay. Sorry. I think I know. There's a beautiful movie, The Boys of Via Panisperna. But that movie probably can be found dubbed in. It's worth seeing it if you guys can call it. Ragazzi di Via Panisperna. Anybody learn some Italian?
Così.
Okay. Well, you're busy with the diploma, but if you're Spanish speaking, then it's really easy. You know, I've learned my Spanish in 3 months after learning Italian. It was almost for free. Okay. The only thing you make a lot of mistakes because it's so similar, but at least it's the same structure. Okay. If you see it in the original version, it's even. It's the story mostly of this genius Majorana and Fermi, obviously. Fermi is the father of the school, and Majorana. I'll talk a lot about Majorana. Tell me another process, please, of lepton flare violation that will have the same suppression, so I don't want to. I know this without doing a calculation, okay, just to see what could happen. What could muon decay without violating charge? Well, it's very heavy, so it could decay even into this. it's interesting that this is sort of a different kind of process you look at. Again, the same branching ratios. We had the level of these branching ratios for delta lepton flavor, all of them around 10 to the minus 13. This is interesting. There is something which is immune to electron conversion in atoms, okay? Similar process, maybe we will come back and talk in more detail. So there are a bunch of interesting physics. Then we can think of tau decaying. Now there are more generations, okay? We should and why we should set the limits on tau decays are worse than the, right? Because if I think of tau, tau immediately can decay into mu plus mu bar. There are now all kinds of possibilities, right? Mu plus E bar, mu plus E bar, and so on and so forth, right? If I'm not forgetting. The limits are worse, I think, around 10 to the minus 8, 10 to the minus 9. But you may get some enhancement in your new theory, because decay also depends on the mass. Heavier particle decays faster, right? For example, just you helped me. What is the, okay, let's see the power of it, estimation. What is the gamma for this process estimated? Well, let's just write here, gamma mu. This is the main process. If I'm lazy, how will I estimate this? It goes through the exchange of W, right? Emission and absorption. Mu enters. Mu goes out. Electron goes out. Nu E goes in. That's nu E bar going out. So this will be G Fermi squared. Good. Okay. Two. Right. Dimension of grounds.
Yes.
Decay rate is a dimension of mass. Okay. Well, coefficients are important because this coefficient here is 1 over 192 pi cubed. That's a small number. Okay. So you see how sensitive it is to the particle mass. Tau will decay. It's more than an order of magnitude heavier, so it will decay 5 orders of magnitude faster with the same physical process. So today we know that there is flavor violation, but it has only been seen in neutrino oscillation. Unfortunately, not in the similar decay rates. One thing that we know here, and we should have summarized it today, we talked about it. This was one thing which was important, that the physical processes must be proportional. For example, this dimensionless number would come out. The other thing is, of course, that there is CP violation in the quark sector because of the Kobayashi-Maskawa phase. And why did we search so desperately for phase when after 3 generations? If I write the weak interaction charged weak interaction, the W current, it looks like this, G over square root of. This is G over square root of 2 U bar gamma mu 1 plus gamma 5 over 2 dW mu plus, which is G over square root of 2. He picks up only the upper component, right? Spinner, I can write as U L U R. So up and down is, okay, you agree? The notation we use with mine. So it becomes UL dagger sigma mu bar. There will be DL. You see the problem with the notation, so I should. Why don't we just say that from here? Why don't we say like this, that what it does to us, it brings the process, it brings the coupling. And then we said, of course, in general, here, I have particle I becoming J through Vij mixing, right? So what I have is some coefficient Cij, G times Vij, Ui dagger, sigma mu bar, Uj, W mu dagger, plus. You agree? Where Cij is G over square root of 2 Vij. Now, how does, I just want to see quickly how much you remember, okay? This you have studied, but I want to be sure, okay? Under CP, under P, what does psi go into? The 4-component spinner. Gamma 0 phi. You check it again in the first homework. Psi goes into C psi bar transpose, which we said I gamma 2. Gamma 2. There are two gamma zeros. Okay, gamma 0. Gamma 0 from here. Psi star. I gamma 2 psi star. So under CP, psi goes into I gamma 2 gamma 0 psi star. Now notice I gamma 2 gamma 0 becomes diagonal. Okay, this is important. This is off diagonal. This is why by under charge conjugation left goes into right. Charge conjugation is like parity, takes left to right. They're maximally broken in the standard model. These two symmetries interchange UL and UR when psi can be written UL, UR. Charge conjugation UL with UR star, but the main point is it takes you from up to down, okay? This is diagonal, however, so this is what? This is I sigma 2, 0, 0, minus I sigma 2, psi star. Right? Gamma 2 is off diagonal, and gamma 0 is off diagonal. This is why CP could be a good symmetry, and basically why it is, to a large degree, a good symmetry in the standard model. Because we stay inside. You see, parity cannot be a good symmetry because it will take you, it will take this out of the space of left-handed.
Yes.
From your parity, I don't have to check anything. Okay, it simply cannot be in charge conjugate. But CP could be. So under CP, this would go into what? Very briefly, this will go into Cij. It would go I sigma 2 Ui star dagger, right? Ui goes into I sigma 2 Ui star. Sigma mu bar I sigma 2 Uj W mu plus prime. W transforms under CP, right? We'll think about it in a moment. But you agree, this is what I would get by this transformation problem. Which is Cij. Then this is minus I. So I'll get Ui transpose. Sigma 2. There is minus I, but there is plus I here. Sigma 2, sigma mu bar, sigma 2, Uj star. I forgot star here. W mu plus prime. What is this? Well, I should commute ui and uj. So this is Cij, uj dagger minus I, the anti-commute. Sigma 2, sigma mu bar, sigma 2 transpose, I'm transposing it, ui, w mu plus prime. Which is minus Cij. What about this? What is this? The zeroth component. What is sigma mu bar?
Minus
Is sigma 0
1.
minus sigma I, which is 1 minus sigma I. So sigma 2 goes through sigma 0. So that will give me 1.
Sigma u star.
What about with sigma I? Sigma 1 and 3 transpose is sigma 1, 3. But sigma 2 anti-commutes with that. And sigma 2 transpose is minus sigma 2. So I get an extra minus sign. So I'll get uj dagger. So let me write like this. There'll be sigma 0 and not, but plus sigma I. Okay, I'm not going to write it in a, and then w mu plus prime. But how much you remember about charge conjugation? How does photon transform under charge conjugation?
Minus.
Very good. Under P, AI goes into may I, A0, A0. So by sheer analogy, under charge conjugation, W plus mu goes into minus W mu minus charge conjugation. Particle goes into antiparticle, picks up the minus sign. The gauge boson picks up the minus sign from the current interaction, just like the photon. Okay. And under P, same as everybody. As photon, W0 goes into W0 and WI. And of course, charge is not changed. So under CP, W0 plus goes into minus W0 plus. And WI plus, no, minus. Charge conjugation is there. And WI plus goes into minus WI minus. So you see, I changed the sign here. I had a minus sign here. And where there is a W0, there will be, in other words, there will be minus W0 plus WI minus. Minus sign and minus sign. I'm back to Cij, uj dagger, sigma mu bar, ui, w mu minus. Under CP, this thing goes into this. It's on what it did. It reversed the position of the first and the second spinner, and W plus into W minus. Let's summarize it here.
Why sigma bar?
Sorry?
Why sigma bar?
Not a bar. It should be sigma mu.
Sigma.
No, I think it should be sigma mu bar. Look, I have, it became sigma mu apparently, but there is an extra minus sign between two guys.
Yeah.
There's an overall minus sign which I took into account, so I got plus W0, and okay, I could have written like this, plus sign. So it tells me that I'm back to sigma mu bar.
Yeah.
So that UI dagger, Cij, sigma mu bar, Uj, W mu plus, goes under Cp into Cij, Uj dagger, sigma mu bar, Ui, W mu minus. But the original interaction was, by the weak Lagrangian, let me write it, was Cij, Uij, sigma mu bar, Uj, W mu plus Commission conjugate, which was Cij star, Uj dagger, sigma mu bar, Ui, W mu minus. Remember when you have the Hermitian conjugate, it's always left-handed. Left-handed stays left-handed because of gamma zero and everything. Okay, when you do that, so sigma mu bar stays sigma mu bar. Sigma mu bar becomes the left-handed piece. Okay, that's a very easy thing to verify. So this is the weak Lagrangian, and I just found out that the first guy goes into the same coefficient Cij. So the Cp conservation means real couplings. Okay. Cp implies Cij is Cij star. If I want to have Cp violation, they must be complex. Then Cp may be violated. Remember, there is still no guarantee, because there are actually phases I can play with. We found out that it took a lot of phases to get one physical phase. We had 3 generations. Remember how 3 generations look like? They have 3 mixing angles and 6 phases. And you and I had to do all kinds of shuffling. Well, they did it for us. Kobayashi, Mascabo, or better to say Kyung, did it for us, so that we are left with one phase. But at least this is a must. This is what I was so desperately searching for a CP phase. I need complexity in order to have CP violation. One of the great challenges now in neutrino electronic physics also to see whether the analogous CP violation is taking place. So we'll come back. I just wanted to sort of remind you of this fact that presumably you knew. I would imagine you've done this in a 4-component way probably, or who knows.
Is there another chain?
Sorry?
Is it the indices are another chain? Why is there another chain? Cij equals Cji.
Under CP, this first piece goes into this, but the Lagrangian has Cij star. So if I want to break CP, this should be different from. This is my Lagrangian, okay? So let's be more specific. I can erase this, I hope. So I could have written here, under CP, this goes into Cij, Ui dagger, sigma mu bar, Uj dagger. Well, I don't know, it's written there, so what? I'm repeating myself, I don't know how I can help you. This go into, this first piece goes into this. It doesn't go into what it should go there. This Lagrangian, this is all I can write. I'm not allowed to. Will not be simply conserving this Cij is different from Cij.
Yeah, sorry.
Right. No, it's good, it's good. I want you to wait. And in order to have CP violation, remember what we found out, that the epsilon CP was a product of all mixing angles.
Sorry, question.
So quick reminder here, we'll finish on this. Yes, please, on the leptonic. I'll summarize and then I'll see how much you remember next time. Okay, we won't do that today probably, but
What is epsilon? I mean, it's not if you understand. I mean, you read it before, but I never see it before.
epsilon is a measure of CP violation. So the best way to define it, remember, if CP is a good symmetry, the eigenstates of K boson mass matrix must be K plus and K minus, which is K0 plus minus K0 bar over square root of 2. You agree? How do I know that they have to be eigenstates? Because under CP, K0 goes into K0 bar. So K plus goes into K plus under CP, and K minus goes under CP into K minus. These are CP even and CP odd states. Okay, once again, to remind you, please, I want this. I went briefly because you've studied this before. And that reflected in the fact that then the mass matrix for K and K bar would have the form MK. According to CPT, particles and antiparticles have the same masses. And then there was delta MK, real. Remember, with 2 generations it was real. And the eigenstates were this. It turns out in the experiment we said, and how do I do the experiment? I produce chaos and wait. Just wait. Because tau plus is much smaller than tau minus. About 1 centimeter and about 100 centimeters. So whatever I produce after 1 meter of weight, there's going to be only K minus. And that can decay only, so K plus decays into 2 pi, combination K minus into 3 pi combination in order to produce. So what they found out was that 1 in 1,000 K minus decays into 2 pi. Okay, which means that, so now we define the states which are K long, which would be K minus. I thought this was an eigenstate, but actually it should have a small portion of K plus. Call it epsilon CP. This is a physical state which is long-lived, which I call minus. It has to carry some of this, and that must be 10 to the minus 3. K short was K plus. It carries a little combination orthogonal to that one, or K minus. I don't even have to normalize again because epsilon is very small. In first approximation, epsilon is 0. CP is basically good symmetry of the standard of the low energy phenomenon. That's why it took years after, parity violation was discovered in 1956. And it was an immediate experiment to be done. As soon as T.D. Lee and Yang in the summer of '56 announced this bombshell, that parity, now they paved the way. It may not be a good symmetry. People like Madame Wu and like Lederman sat down in a span of a few months, produced convincing arguments, and it was very simple. All you had to do was right. But you had to think a lot about what to do here. You had to understand very well the. Another thing that you needed to have here is the difference of light time has to do with the fact that the masses of plus and minus are basically the same. Right? The mass difference is so small. This is why the difference is the rates. This decays into 3 pi. It turns that somehow, I don't know if you ask yourself, why is this guy so much longer lived? Let me see if you ask yourself this. After all, they have the same mass. Particles of the same mass decay with the same speed, more or less. The only reason, okay.
Symmetry?
No. No. No, because it does decay. There could be a symmetry, like proton, for example. Well, we don't, you know, symmetry, actually there is a danger to say that symmetry is the argument. You know, proton doesn't decay because of symmetry like baryon number, or there is a symmetry because proton doesn't decay. We should be careful, okay, because you and I will give up on that symmetry tomorrow. When, you see how I'm saying, not if, when, okay? And tomorrow it's going to take some time. We need a new generation of proton decay experiments. I'll bet you that they'll see. It's going to take another 20 years. And you say, am I going to be around to pick up money from me? I'll try to be around.
We have to make a bet.
At least we can. I'll send you, if there are guys of you offering you bets, you know, different social stature and salary. I'll give you odds which are. So, to remind you, what is the lifetime of muon? You knew this number. What about neutron's lifetime? Roughly.
15 minutes.
Yeah, on the order of 10, 15 minutes, right? So what is it in seconds? That's 10 to the 3 seconds. Am I right? Roughly?
No.
1 minute, 60 seconds? Yeah, that's a fair. Yeah, let's take 10 to the 3 seconds. But what is the mass of the muon? 100 MeV. What about neutron mass? So it's 5. It's 1 order of magnitude heavier, so it should decay 5 orders of magnitude faster. According to the formula that you knew, they should go, okay? Yeah, said it, it goes as mu to the 5th power. Why is then the neutron not decaying 5 orders of magnitude faster, but 3 orders of magnitude slower? Same reason that makes K minus decay slowly. In order for you and me to decay, we need a phase space.
It's 15 order.
Huh?
15.
But particles in the final state?
Because it's a wave
Right.
interaction? No, whatever.
No, when you decay, for example, can the Z boson decay into TT bar?
No.
You didn't include that.
No.
Can W decay into TB bar?
No.
Why? Because it's not heavy enough. So what matters obviously is the mass difference of the initial and final state, not your mass. See how careful we have to be, because typically the particle is much heavier than what it decays into, and then it's safe to say that you decay proportional to your mass, whatever power, but it's the mass difference. And the problem is the proton has basically the same mass.
Yes.
So when neutron decays, so it's not a symmetry. We believe that there is this baryon number symmetry. It is true, okay? We believe in it because proton doesn't decay. Okay, we shouldn't use that as an argument. But in this case, there is no symmetry that forbids it. This is the normal weak interaction process, okay? All the quantum numbers are the usual quantum numbers, okay? And they are preserved. And the thing is that the mass of the neutron, the point is barely bigger. The mass difference is 1 MeV. This is where you lose your phase space, okay? Whereas the muon has all these 100 MeV to provide the enormous phase space to decay. And so it happens that M minus is roughly 3 M pi, a little more. Pion is about 140 GeV, so this will be about 420 MeV, sorry. And these guys are around 450 or so on. The phase space there is small. It's not on the order of the mass. It's sufficiently smaller. Okay, there is still some phase space. This is around 450 MeV or something. It's not like neutron. Look how much neutron loses, 9 orders of magnitude. These guys lose only 2 orders of magnitude. But already 2 orders of magnitude is a lot. This is very important. You needed the separation of lifetimes, okay? And you needed to figure out this. So what you needed to figure out, among other things, you needed to figure out the mass difference. How in the world do you measure the mass difference, which is? How would you measure a mass difference so small? Why do I say that the mass difference is 10 to the minus 15 relative? How can I measure that? it surely, we don't have such good scales. And we surely don't have them in the low energy experiments. We don't have scales that can measure mass with that precision. Look at the mass, read the mass of the electron and so on. You won't see that precision, okay? Or better, I ask you, the subject we should sort of remind you of that Smirnov talked about is neutrino oscillation. We measure a tiny thing. Tell me, what neutrino oscillations you know in this? I'm about to wrap it up. Yeah, tell me the processes, physical processes. I don't care about 1, 2, 2, 3. What oscillates? Where did we see oscillations? In
electron neutrino to mu.
No, in which physical processes? What happened?
The sun and the
Sun, okay. The original idea of the core was, if there is oscillation, what does it mean? That the state I produce, which is called nu E in the sun, may not arrive to me, because it may turn into nu mu. It's a long way. It's a long way from sun to here. Which has turned out that its story is very different from what you imagine. Neutrinos tend to oscillate inside the sun. It's called MSW effect. So she's one of the people who's on. So, so I have oscillations in the sun. And you say nu mu goes into, nu E goes into nu mu. What else? Actually, they didn't see this. This took more time. These people started to notice already in the 70s that there was something wrong. Okay. He suggested in the late 50s and developed the whole thing in the early 60s. What the core, the whole, he suggested the mechanism and the oscillations and the sun deficit and developed the theory. Okay. First alone and then with Gribov. What else is there? Right, but which neutrinos? How do we call them? Where did they look at them? Where? From where? From atmosphere, actually. They're called atmospheric neutrino oscillations. How do I get neutrinos in the atmosphere?
Pions that decay to muons.
I get pions. I get from cosmic rays. I get pions that decay into muons. And muons that decay in 10 to the minus 6 seconds. When they are fast moving, they take a longer time to decay, and they may arrive. There are things that to remind you. So atmospheric neutrinos. This was very easy to see because all I had to do is put someone here in a mine in Kamioke mine in Japan, right? And he or she could look for neutrinos coming from here. See, here I could even see oscillations. You see, seeing oscillations in the sun is not so easy because in order to see oscillation, you have to change the distance. It's hard to change the distance from the sun, right? I may do that, different sides of Earth and so on, but a small effect, okay. Here, what I can do, and it's a huge thing, I can look for the neutrinos coming from above. I can look at neutrinos coming from below. I can look at the neutrinos coming from the side. I can do this profound thing, and we actually saw oscillation pattern. Okay, this is a beautiful thing. So what is delta m squared, which is measured here? I just need a few more minutes. Remember, I need extra 10, 15 minutes. We are going to make up this lecture that we are going to lose eventually. Okay.
0.0.
We are about to do it, sorry?
0.005.
Well, it's, if you tell me in 10 to the minus 3, basically, it's good you're more precise. 10 to the minus 3 eV squared. This is atmospheric neutrino mass difference. Okay, it's a very small number. And the sun even, it's interesting. It's not, okay, I'm a bit rough here. It's another couple of orders of magnitude, a bit less, okay. Maybe a factor 1/30, I think. Okay, so these are tiny numbers. So you see, these are these extraordinary tiny numbers. And how would you get an idea to measure them? Where did the Pontecorvo get an idea? Why did he think of oscillations? They saw oscillations before. But you don't put these things together because it's a completely different physics. In K on oscillation.
Okay.
if there are oscillations that I can remind you, today, like in neutrinos, okay, I look for a tiny effect. So we don't actually even have exact proof that neutrinos have the mass. You know how we arrived at the mass being, we rejected all other solutions. The neutrinos behave as they have the mass, but we still didn't measure neutrino mass as directly as you and I would like to measure. The oscillation thing is the sensitivity to the possible change of flavor, which is sort of an indirect thing. You talked about this? Did Alexei?
Yes.
This is why Pontecorvo had an idea, and this is how they measure this very tiny number. Okay, I'll remind you, today is not a good time. From here you could measure this extraordinary thing. The delta and k. Where k is 10 to the minus 15, right? Now here we know that such effect is not so dramatic because we already know that neutrino is less than 1 electron volt. Basically, maybe 2 electron volts from direct searches. How would you search directly? In this final check, you see what we do here. We go through the formalism and then we go through, I try to keep it for those of you. Actually, formalism probably keeps you more awake, okay, but I want you to appreciate it. We have what we do here, we go constantly from formalism applying to phenomena, we try to disentangle and then try to think carefully. How would you look for the neutrino mass? So, Jorge knows something that I don't know if you other guys, or maybe Alexei talked about. The possibility that there is lepton number violation. Yes. The lepton number violation is there. What we would hope to see is that, but that's only if lepton number is violated, that 2 neutrons who simultaneously decay into 2 protons plus 2 electrons. Normally this happens. This is a very, very rare process, by the way. Takes about 10 to the 21 years. You have the simultaneous probability of 2 neutrons decaying into a nucleus. Okay, so T2n is roughly 10 to the 21 years, and this is what happens. But it's the opposite from the way neutrino was found. If there is lepton number violation, then I don't need neutrinos that are always needed, in principle. Then, you know, the way neutrinos were discovered, I will now discover, but the opposite thing. Instead of seeing a continuous spectrum in electrons coming out, now I should just keep the fixed energy if there are no neutrinos coming out. So this is how they are looking for neutrinos double beta decay. This turns out, now I asked you about the mass, and you mentioned to me a physical process of lepton number violation. Why? What does it have to do with the mass? It turns out that this process would take place automatically if neutrino has what is called a Majorana mass, which violates lepton number. A neutrino may not have Majorana mass. So how would I measure neutrino mass?
Directly.
It's very interesting that the limits are similar. Here people will you know, when they put a limit on this process of neutrinoless, the name is terrible, it sounds like a cryptic thing. It's a beautiful, fantastic new discovery of violation or not of the basic laws that we've been looking this for now, dreamt about from the very moment. Only a few months later people started to think about it when Majorana threw his bombshell in 1937. The last paper before his disappearing, one of the few papers that he published, saying that this would happen. One was desperately searching for this process, okay? And you don't see, so you put an upper limit. 0 nu 2 beta, we call it. 0 neutrinos, 2 beta. It's bigger now than 10 to the 24, getting to 10 to the 25 years. Equivalently, this funny Majorana mass that we have to remind you of should be less than, so the numbers vary depending how much you trust nuclear physics calculation. But they all seem to agree that there is this, and they cite it even as better than this. Interesting. Direct search is also the same number, basically. But how would you search directly? Well, you look at the distribution of the electron energies in the, when you are near the end point, okay, it's too late to go on, you should stop. Do you remember that? Near the end point, you start to get sensitive to neutrino mass.
Yeah, I can't remember it.
The neutrino, the way that we decided neutrino had to exist, that the distribution of energy of the electron didn't, it peaked somewhere, and then when you go down to here, you start to be sensitive to neutrino mass. You have to get there close to the zero, okay? Then this tiny number, because it looks strange, how in the world you're going to measure that? These are very, these are beautiful experiments, right? In the old-fashioned, real high precision experiment, not the detectors with thousands of people, Here also, and this is sensitive to any mass. It doesn't matter whether it's so-called Dirac or Majorana, as long as the neutrino has a mass. According to Einstein, by mass, I always mean this. So we put the limit similar to 1 electron volt. Okay. So it seems to me, what I'm getting from the last half an hour of sort of more chatting, then, that I should remind you maybe of neutrino oscillations and of Majorana mass. It seems to be safe to assume that it's not that fresh. Because what you and I have to face is how to account for neutrino mass in the standard model. So what did you, I stop here. Just tell me, what did you learn? Well, let's stop.
Okay.
You can ask me some informal question.